Don't forget to like and subscribe. Greenbelt, Maryland for months. Inside the towering Building 29 here at Goddard Space Flight Center, the 4 scientific instruments at the heart of the James Webb Space Telescope, JWST, or Webb, have been sealed in what looks like a house-sized pressure cooker. A rhythmic chirp 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 sounds as vacuum pumps keep the interior at a space-like 10 billionth of an atmosphere, while helium cools it to 250 degrees centigrade. Inside, the instruments, bolted to the framework that will hold them in space, are bathed in infrared light focused and diffuse in laser-like needles and uniform beams to test their response. The pressure cooker is an apt metaphor for the whole project. Webb is the biggest, most complex, and most expensive science mission that NASA has ever attempted, and expectations among astronomers and the public are huge. Webb will have 100 times the sensitivity of the Hubble Space Telescope. It will be able to look into the universe's infancy, when the very first galaxies were forming, study the birth of stars and their planetary systems, and analyze the atmospheres of exoplanets, perhaps even detecting signs of life. If you put something this powerful into space, who knows what we can find? It's going to be revolutionary because it's so powerful, says Matt Mountain, director of the Association of Universities for Research in Astronomy in Washington, D.C., and former JWST telescope scientist. Like that of Hubble, however, Webb's construction has been plagued by redesigns, schedule slips, and cost overruns that have strained relationships with contractors, partners in Canada and Europe, and most crucially supporters in the U.S. Congress. Other missions had to be slowed or put on ice, as Webb consumed available resources. A crisis in 2010 and 2011 almost saw it cancelled, although lately the project has largely kept within its schedule and budget, now about $8 billion. One of Webb's gold-coated beryllium mirror segments is inspected before assembly at NASA's Goddard Space Flight Center. NASA Chris Gunn, KW Don, University of Arizona. But plenty could go wrong between now and the moment in late 2018, when the telescope begins sending back data from its vantage point 1.5 million kilometers from Earth. It faces the stresses of launch, the intricate unfurling of its mirror and sunshield, after it emerges from its chrysalis-like launch fairing, and the possibility of failure in its many cutting-edge technologies. Unlike Hubble, saved by a space shuttle mission that repaired its faulty optics, it is too far from Earth to fix. And not just the future of space-based astronomy, but also NASA's ability to build complex science missions, depends on its success. That's why those instruments sat in Goddard's pressure cooker for what is known as Cryovacuum Test 3, CV3. And it is why Webb's other components, including the mirror and telescope structure, the bus that will supply power and control the telescope, and the tennis court-sized, multi-layer parasol that will help keep it cool, must undergo a gauntlet of testing, alone and in combinations, until the whole spacecraft is ready. For those on the inside, the strain will only increase as assembly continues, the tests get bigger and more comprehensive, and the spacecraft is launched into space. Only when Webb opens its eye and successfully focuses on its first star will the strain be released. In the mid-1990s, after Hubble had had its optics corrected and was busy revolutionizing astronomy, researchers began planning its successor. The catchphrase in NASA at the time, championed by agency chief Daniel Goldin, was faster, better, cheaper. Goldin challenged NASA engineers and the astronomical community to come up with a follow-on that was cheaper than Hubble, but bigger, with a mere 8 meters across. He received a standing ovation when he described the plans to the American Astronomical Society in 1996. Whereas Hubble covered the whole range of visible light, plus a smidgen of ultraviolet and infrared, the next-generation space telescope, as it was then known, would be a dedicated infrared observatory. If you put something this powerful into space, who knows what we can find? It's going to be revolutionary because it's so powerful. For astronomers, the infrared spectrum was a beckoning frontier, visible light from the most distant objects in the universe. The very first stars and galaxies that formed after the Big Bang get stretched so much by the expansion of the universe that it ends up in the infrared range. By the time it reaches us, many chemical signatures in exoplanet atmospheres also show themselves in the infrared region. Yet Earth's atmosphere blocks most infrared. Webb will give us the first high-definition view of the mid-infrared universe, says Matt Greenhouse, JWST project scientist for the instrument payload at Goddard. Don't forget to like and subscribe.